Hey friends, I'm here at my office at UC San Diego, and I just recorded an episode with none other than Sheldon Glashow, young Sheldon, old Sheldon, winner of the 1979 Nobel Prize in Physics. He's a towering figure in physics and a generous, gentle soul. I had so much fun with him. I asked him to give a report card about the state of physics, how it's changed since 1979 when he won his Nobel Prize, and you won't want to miss his answer to that question. You'll be surprised at the letter grade he gives to physics. And you'll get a fascinating glimpse into a very, very interesting character who is going to play a role in my upcoming book, which is coming soon, tentatively titled Lessons from Laureates. And you'll find out more about that and all the good stuff you are going to learn from these brilliant guests that I'm so privileged to have on the show. Stick to the end of the episode if you want to hear how Shelly lost $1 and 27 years worth of interest to Eric Weinstein. You'll also find out Aunt Shelly's answer to the question that I asked him, which I considered the most important question I've ever asked a guest on my show.
Any sufficiently advanced technology is indistinguishable from magic.
Welcome, everybody, to this episode of the Into the Impossible podcast. I am your fearful host, Brian Keating, co-director of the Arthur C. Clarke Center for Human Imagination. And today we have a very special guest who is not only an icon in the field of physics of all different varieties, but also a huge science fiction fan. And I hope to discuss with my guest, Sheldon Glashow, emeritus professor at Harvard and currently the Metcalf Professor of Mathematics and Physics at Boston University.
Oh, no, I'm also retired from that one.
Oh, you are? Okay. So do you get two emeritus salaries? Very good. In 1961, Sheldon Glashow extended the Electroweak unification models due to Schwinger, his PhD advisor, who we'll get into today. And he did so by including a neutral current that operated at short ranges. We'll talk about that, the Z naught. And the symmetry that resulted was originally depicted as SU2 cross U1. We'll talk about what that means. And where things go from here in physics, perhaps extending if Shelly has time to SU5 and beyond. We'll keep it as technical as Shelly's willing to go. I've got a lot of questions of my own. And most importantly, I want to just thank you for coming on the Into the Impossible podcast, where we talk about all sorts of matters, not just physics, but this is sort of Nobel Prize week, where you have on Barry Barish tomorrow, and we had on Adam Rees last week, and next week we'll have...
Barry is tomorrow?
Barry's on the show tomorrow. He's recording a second episode, and we also have some of your friends and acolytes that you inspired. People like Frank Wilczek are coming on, as well as Kamran Vafa. And we've had on some really spectacular guests. Yesterday, we had on Lenny Susskind, who has a deep connection to Shelly. And I wanted to start there because one of the things that strikes me about your book, which we'll talk a lot about, Interactions, it's just a lovely book. It's now about 32 years old. Hard to believe. But I remember seeing this book when it came out and only finished it a couple hours ago, but it was well worth it. And it's still timely as ever. And I want to get into that, including this very fascinating scorecard, almost a report card for physics that you gave as an assignment in 1988 when this book first came out. And I want to ask you what kind of grade, both theoretical particle physics, string theory, and my field of experimental cosmology, what kind of grade we would be getting against these very difficult, challenging homework assignments that you gave the field back in 1988. But first, let's start with your with your interactions with Lenny Susskind, who was on the show yesterday. And Lenny said to give regards to Shelly and say, how's the plumbing job holding up in your 50-year-old house in Brookline, Massachusetts?
Yeah, he was here, and of course we share the fact that that his father and my father were both in the plumbing profession. Actually, my father employed plumbers, and he had a little plumbing concern on 1622 Amsterdam Avenue in New York, which amazingly enough still exists, although my father died in 1962 and had sold the company to his foreman, or given it to him effectively in the 1950s. But the white trucks that patrol New York are called Glashow and Company, and they're still there with the same name. As my father always said, reputation is very important.
Yes.
His reputation lives on as a plumber. Mine does not. So I had some plumbing problem that I had to call on a real plumber to fix. Actually, I didn't pay this particular plumber. At another occasion, though, it was a Christmas Eve, and we had a flood in our bathroom, and it was a mess. So I turned off the water in the house, and I dredged up my old memories of how to wipe a joint, which is an old way of fixing a pipe when you have a broken pipe, is you take some molten lead and pour it around and wrap it with your hand in a glove. You sort of wrap the joint with melted lead, and it worked. And it also has lasted for now something like 47 years. So I too can still plumb a bit.
You missed your calling potentially as an experimentalist. There's a lot of piping and tubing involved in the LIGO experiment. I'll be talking with Barry about tomorrow. The LIGO experiment being a 4-kilometer evacuated plumbing pipe in Louisiana and Washington. So maybe you could have, maybe can have a second career, who knows, following in the family tradition. But the other thing you share in common with Lenny, of course, is that you both attended not only Cornell, but the Bronx Science, which is has more Nobel laureate alumni than some countries on Earth. And I want to first start
Seven
with
of them, actually.
Yeah, and that's really a phenomenal record. Of course, you won the Nobel Prize in 1979. And we'll talk about that and the effect that it had. But first, you know, your father really plays a big role in this podcast, and it reminds me of a conversation I had with Jim Simons, who is from the Boston area, not from the New York area, but he currently lives there. And he told me once that, you know, plumbers don't get enough respect and attention. In fact, once he had to call a plumber for a late night repair, and he called the plumber comes over, and 15 minutes of work, he says, that'll be $400. And Jim says, you know, $400, what'd you do? I'm a hedge fund manager. You know, I make barely $3,200 an hour. You work for 15 minutes, that's $3,200 an hour. And the plumber says to Jim Simons, oh yeah, you make $3,200? That's what I used to make when I was a hedge fund manager. So sometimes we should not overlook the importance of plumbing. But your father plays a big role, and of course he passed away in, you said, 1962, which is barely a year after your really eventual Nobel Prize winning discovery. What do you think he would have made of the festivities and kind of the level that you ascended to in science? Would he have appreciated it? He played such a big role in your life, as you described.
Oh, yes, he would certainly have appreciated it. He was himself frustrated because he never managed to go to college, or at least complete college. He started in at Cooper Union, but never quite had the time with a young family to feed. He had to do his plumbing. So yeah, he would have been very appreciative had he lived. But unfortunately, I lost him. He had many stories to tell about plumbing, one of which I will tell, if I may.
Yes.
He came back saying, well, one day he was called on by some woman in a luxury apartment on Fifth Avenue, and she called him and said, I would like you to install a bidet in my apartment. And he said, of course, a bidet. I will certainly do that. Let's make an appointment. And which he did in the future, because he had no idea of what a bidet might be, being a Russian immigrant, and he just didn't have experience with such things. So he asked his friends and finally was able to find a bidet and installed it. The woman was very satisfied, and maybe he got $400 for that.
Yes, it's you never know how valuable they are until you need them. But I want to talk a little bit more about the role that collaboration played in your life. This book, in really contradistinction to Lenny's book, My Black Hole War with Stephen Hawking, that we discussed on the podcast. He speaks of collaboration too, but it's almost in the sense of wanting to have a rival, not a nemesis, like an evil villain, but to have someone that you are trying to always outdo. And I see, you talk about your lifelong friendships with Steven Weinberg and with others, as well as recounted throughout, and your almost paternal, father-son relationship with Schwinger. I sense very little of adversarial or nemesis content in this book. And I wonder, is there a role for sort of a rival as a theoretical physicist that we often have it in experiment? We're trying not to get scooped. We're trying not to get beaten by other experiments. Does having a rival in theoretical physics, is that anathema to that practice, or is it something that could be healthy if used properly?
No, I've not had much experience with rivals in theoretical physics. It's always been, for me, a cooperative endeavor. For example, with Steve Weinberg, we, of course, not only went to high school together, but we went to college together as well. And were both professors at the University of California for a few years together. We wrote a couple of excellent papers, at least 2, maybe 3. Then we did fall apart for a while. We had our differences for reasons which are not related to physics. But that's the closest I would have to, I wouldn't call him a rival. It's just someone in physics with whom I had personal differences. No. It's been cooperative all the way. I think, for example, of my long-term relationship with Sidney Coleman, who, by the way, was a much more avid science fiction. He even published science fiction criticism. He had a partial owner of a publishing company, Advent Publishers. Well, I have my minor claim is in high school, I was one of the editors of the first science fiction high school fanzine, but that was as close as I came to publishing science fiction. So with Sydney, I had my first interesting papers written. We were inspired by Murray Gell-Mann's eightfold wave theory. So we showed how you can do things with 3x3 matrices that others used 8x8 matrices. We felt very confident about that, and we had our only eponymous formula, the Coleman-Glashow formula, which was once interesting, has sort of lost interest today. Anyway, then we came back. Sidney and I went our own ways and did different things for many, many years. And just before he retired from Harvard, is already showing symptoms of the disease that would eventually kill him. We wrote a series of papers on testing Einstein's special theory of relativity. And these were great. So here's a man that I collaborated with at the very beginning of his career and at the very end of his career, but cooperative always.
And speaking of science fiction, if I recall correctly, you're related to this gentleman. This is Carl Sagan in finger puppet form. We have to get you a finger puppet version. I have one of him. I have one of Galileo Galilei and one of Einstein. But of course, Carl Sagan wrote science fiction, proper hard science fiction, as well as being a foremost, exponent of science nonfiction. Can you talk a little bit about, well, first of all, how you are related to the late, great Carl Sagan, whose widow has been on my podcast, as well as his daughter, Sasha Sagan. She's a writer in her own right, so the apple did not fall from the cosmic apple tree. So can you talk about the impact of science fiction on you and how it may have influenced you, maybe not, to take the career path that you did take?
Well, yes, so of course, Carl comes rather later in my career than science fiction. Carl was married to, well, my wife has or had 3 sisters, and one of those sisters Lynn Margulies, was the first wife of Carl Sagan. In fact, it was the greatest contribution Carl Sagan made to science was to get Lynn, who was a history or literature major, to switch to biology. And she became very well known in biology with a rather mixed reputation for a while, because some people thought that the things that she was doing were quite crazy. They became textbook accomplishments, and at the end of her life, she was widely acclaimed as a very fine biologist. Anyway, that was Lynn, and that was how I knew Carl. Carl came by once to Harvard. He was already at Cornell. He was doing research on whether there could be life on Mars or something like that. He ran into a mathematical problem that he couldn't solve. So he asked Sydney to solve it for him, which he did. It was essentially trivial. Just like Lynn was not very talented mathematically, nor was Carl. Anyway, the problem solved. Carl wrote a paper, and then Sydney was absolutely flabbergasted to discover that he had written a paper with Carl on the possibility of life on Mars.
That's every science fiction fan's dream, is to inadvertently discover some possibility for life on Mars.
Yeah, no, science fiction was an important part of my life when I was, like, say, 12, 13, 14. I read astounding science fiction religiously from more or less 1944 to the 1960. Well, I don't know if it lasted that long, but that was, yes, it was very important. For example, there was a column in Astounding Science Fiction called Brass Tacks, which talked about science. And it was there that I learned about the possibility of atomic bombs before the explosions that took place in Japan. Yes, I can say that science fiction got me, to some extent, got me into science. My brothers were also responsible in various measures, but science fiction played a significant role. And I still appreciate it. I will occasionally read science fiction, but not that often.
Right. Yeah, I always find the attraction and kind of the limited time available to want to understand more about science nonfiction while I can, and hopefully can make some contributions. I want to talk about the role of teachers in your life. You speak very in very glowing terms, obviously, about Schwinger, and really about his generosity of time, of attention. You know, mentoring a dozen students at once at one point, including you. And I just, you know, I'm an experimentalist. The most students I've ever had is about 6. And that's even kind of impossible to imagine. What was he like as a teacher, as a mentor, and not just as a physicist?
Well, yes, he spent a lot of time with, by having 12 or 13 students at a time. But a corollary is that he didn't spend very much time with any one student. I did not get to speak with him much about my thesis. When I and my friends invaded his office to get thesis subjects, I was at the end of the line, so he gave me something that was rather speculative. He more or less said, go and unify a weak in electromagnetic interactions. But I had no idea how to do that. But he didn't have a great deal of assistance to give me. Consequently, I didn't manage to get very far either. I did a few things which convinced me, and perhaps convinced Julian, that there was a possible road toward a unified theory of weak and electromagnetic interactions, but I had not found that road. He was a very kind man. He would, on several occasions, bring me to his home where his wife would entertain us, serve a very nice dinner. But altogether, perhaps during my college career, aside from having lunches where we didn't discuss science, I must have spent no more than 2 hours with him for advice and encouragement.
Oh, wow, that's a pretty impressively short amount of time. I'm going to tell that to my students who complain about me spending that much time with them per week. I want to talk also about the role of ego in science and whether or not it is not only pernicious, as it certainly can be, but can lead to this, level of confidence as well to pursue ideas, even when they're likely to be wrong. You don't strike me as a person from the what I've observed, and you're very candid. The book is hilarious, and I think it should be required reading. I'm mentoring a young student. Actually, he's a young child of one of your. A person that you made a bet with, Eric Weinstein. Apparently made a $1 bet. He was telling me that was paid off 27 years later, but not with interest. So maybe we'll get into that. But anyway, his son Zev is quite brilliant, and I've assigned his son Zev, who I'm mentoring for some research projects. He's 15 years old. I've assigned him to read Interactions because it's so good at explaining what was known in as of 1988 and. Depressingly, there's only a few things that have been added to this canon. But the one thing that strikes me is how honest, how hilarious, just how magnanimous you are in your writing. And I think it's so commendable. It makes it very easy to read, very easy to understand. And yet, I suspect there is a role of ego in your life to really do things and have a courage to pursue things. Can you say, the role that confidence, if you will, plays in theoretical physics?
The role of ego, and it's hard to address that subject. Let me say rather that what I found doing science to be a lot of fun. I began doing real science, perhaps as a graduate student. I wrote a paper with an experimental physicist at that time. It wasn't a very good paper, but it got me in the game. When I went off to Copenhagen after completing my studies with Julian Schwinger, that was the Niels Bohr Institute, I spent 2 years there on and off, sharing the time at CERN. But what I discovered at Copenhagen was a plethora of graduate students, postdoctoral students from many countries, from China, from Russia, from Japan, from Eastern European countries. Close friends I made with a Polish scientist, a Czech scientist, Italian, et cetera, and wrote a paper with papers with them, papers with Norwegian scientists, Swedish scientists. What I realized is that their cooperation is the name of the game. And when I went, while at Copenhagen, it was at Copenhagen, by the way, in the spring of 1960, that I had the idea of the SU2 cross U1 theory, and wrote the paper in 1960, sent it into a journal called Nuclear Physics, which takes its time about publication. So although I submitted it in the spring of 1960, it was published in 1961. So it's really in 1960 that I did that work. Question of ego, there it is. But the next great moment in my life was meeting Sidney Coleman as a postdoc at Caltech. Things were so different than in physics. I was having a ball traveling between my lady friend in Geneva and my lady friend in Copenhagen, and stopping in Germany, typically on the way, and picking up a couple $100 for giving a talk. I had and enabling me, for example, to buy a TR3 while there, so I could commute more easily and more rapidly. I was having so much fun. which is the name of the game as far as I'm concerned in science. And it's always been that way ever since. So science is fun. The science I did with John Iliopoulos, which led to the Glashow-Iliopoulos-Mayani paper, of which I'm very proud, emerged in part on the beaches of Mexico while we were both participating in some summer school, swimming around in the ocean, and he was also a scuba diver as well. We came upon our ideas. And it was fun all the way along. And one of the things I enjoyed most about my career in science is there was usually a time when I knew something that my peers did not. That is to say, when at the time that Murray introduced SU3, flavor SU3, the Eightfold Way, it was obviously correct, in my opinion, and in Sydney's opinion. We knew that this theory was right. They didn't. So we talked all over the world, in fact, lectured about the wonderful theory that had to be true. And sure enough, 3 years after it was invented, it was proven to be true by the work of my experimental friend, Nick Samios, at Brookhaven Lab, finding the omega minus particle, the missing particle. So it's always been fun. And when I suggested my biggest embarrassment, personal embarrassment, was this, that when in 1964, I returned to Copenhagen, I worked with James Bjorkane, and we published a paper which introduced the idea of the charmed quark, including naming the damn thing. And I then promptly forgot about that work. At the time that we invented it, I didn't realize that it was an essential step in expanding the electroweak theory that I had previously worked on to make it apply to nuclear matter as well as to leptons. The theory that I talked about and that Steve Weinberg talked about was a theory of leptons. And I simply didn't recognize that this was the key to it all until I collaborated with Mayani and Iliopoulos, and we realized that the charmed quark could realize its name. When we named it, I named it randomly charm. I don't know why I picked that word, but charm it was. It was a thing that averted evil, the evil being the strangeness changing neutral currents that don't exist. So
right.
that
you explain that
yeah. About that there,
yeah, how charm works. It's rather charming. And you also talk about Iliopoulos, and you recruited him, right? You were basically one of the people responsible.
I also recruited Alvaro de Rujula, who also was a very important participant in my research career. I was not it was the department that chose Howard Georgi, but he also turned out to be a very important ingredient in my career. I think I've written over 30 papers with each of those people.
If you're liking this video so far, make sure to subscribe and hit the notification bell. I put out videos at least once a week, and I'm here to show the human side of scientists. Despite the stereotypes, we are human beings. My mission is to increase curiosity and engage a multiverse of magnificent minds. I also do subscriber-only giveaways frequently, and I give away copies of books by my guests and other cool things like signed papers by Nobel Prize winners and so forth. So don't miss out on that. Subscribe and hit the notification bell. Talk about recognizing, traits or potential greatness in a young scientist. How did you approach it? Was it more just you had a connection, or are there metrics? Are there quantitative, tracers that bespeak of a potential of a future young colleague?
Well, our choice of postdocs was, when I was at Harvard, was very democratic. So basically, we discussed the matter and came upon our favorite choices. We were lucky. We hit upon the right people at the right time. I can't a posteriori explain why we had the right postdocs, but throughout my career, I and my friends picked a long series of wonderful scientists to join us.
And that the characteristic that really strikes me in here is one of collaboration and congeniality. And I wonder how connected you are to it in your emeritus phase. But one of the biggest blows to physics due to COVID, aside from the awful human toll it's taken, and tragic at that, but it's the lack of in-person gatherings of conferences. You talk of conference or meeting or sabbatical or travel on almost every page of this book. And yes, it seems to me there might be some permanent damage due to physics, at least for some younger generation of physicists. At least I got to participate in it, but I feel that it's very unfortunate that young physicists are not experiencing the types of gatherings that you spoke about in this book. And the role of collaboration looms large in this book. There's very little I did this. It's always how, when this fortuitous, serendipitous partnership with somebody because of a sabbatical, or because of a conference held somewhere, led to a great paper and a great result. So I feel physics has lost that, and it's not clear when it's coming back. All our conferences are remote like this.
Yes, and this year I was supposed to be in Italy. I was supposed to be for reasons of physics. I was supposed to be a judge for a prize in Spain, which had to take place remotely. I was supposed to be in China on several occasions. All of these things had been canceled, not to speak of vacations in Mexico and such. So yes, there's no question that this COVID has had a terrible effect, and continues to. Just today, for example, the schools in New York City were announced to close beginning tomorrow or something very soon.
Yeah, we've even in Southern California have been quite afflicted by it. All our public schools have been closed for a very long time.
I have two grandchildren, a grandson and a granddaughter, who were both students at Washington University in St. Louis. Mm. They're having a wonderful time, but it's not the usual college experience. Mm-hmm. They're making the best of it, and they're going to some physical classes, but many of the classes are remote.
Yeah.
It's just the same.
I want to ask, just getting back to these different personalities that you interacted with. You talk in the book about some people that, for example, Schwinger. You point out how he was, how his personality lent itself. It was sort of a coolness about him, a distance about him. I see other people nowadays, that can be really challenging the orthodoxy of standard concepts in physics, as I think you did. I mean, you were one of the early, not I want to say opponents, but conscientious objectors to string theory, and certainly I want to get into that. But it also takes a certain amount of courage, and I wonder, in an age of social media, which I don't think you have a Twitter account that I know about.
No, I don't.
But the ideas that are originally tentative that would have seen the light of day and maybe gotten a little bit more nourishment in previous generations. Now, because of Twitter, instantaneous, you can basically almost humiliate somebody's idea long before it gets out of the infant mortality stage. And I wonder, if you've observed anything negative in the trend. I mean, it's not only positive benefits of technology getting better and better, but are there negatives that impede scientific progress, especially in high energy or particle physics, that you've observed?
I'm not a fancier of the social media in any respect, but I don't. I can speak of many of deleterious effects that the social media may have had, but not upon the progress of science. I don't see that there's been that people come up with theories and spread them on social media and have them take over. No, that doesn't happen, fortunately. We have, of course, we have our own social medium, which is the distribution of research on the web.
Yes.
But what's called the archive. Now that is a marvelous development of my physicist friend, Paul, what's his name?
Ginsburg.
And has revolutionized the progress of physics because it's enabled people in countries in poorer countries to be able to access what's going on. Every day they have deposited in their mailbox the latest articles that have been written, and it's open and accessible and free to all the world. So that's massively encouraged science, worldwide science, throughout the world.
And the ability to teach and to disseminate lectures from Harvard, from MIT, from UC San Diego. In fact, I want to bring you greetings from my friend, Professor Stefan Alexander, who is the president of the National Society of Black Physicists. And he calls you one of his heroes. He's a professor at Brown University now. And you taught at a summer school, I guess, that he attended as a young man of only 15 years old. And nowadays, that such a thing could be done on the internet. And I want to hearken to page 167 in Interactions. You talk about the dual function of the professor. It's to teach, but also to do research, but actually teaching can improve your research. In fact, you say the best researchers in some countries, such as the Soviet Union, the best researchers are secreted in research institutions where they do not teach. And the university professors are not encouraged to do research. I found that ironic because one of my friends is Russian, and he says that if you translate the word scientist from Russian to English, it basically means someone who was taught. It means a person who was educated, or it's taught. That's what it means to be a scientist. Why do you think of teaching as sort of a secret tool or a secret weapon of the West, at least in terms of improving your research?
Well, it's the American tradition and the British tradition that researchers are teachers almost always. It is not necessarily true in countries like Germany, where there have been a great deal of research is done at research institutes that do not teach. Mm-hmm. Germany has not suffered terribly from this procedure. I think teaching and research go together neatly, but they don't have to. They can be separated. And I probably would have done even more research had I not the responsibilities of teaching, but I probably wouldn't have been as happy, because seeing how these kids learn when they do, which isn't always, is very beautiful. And I've had some wonderful, taught some wonderful students, and that's been an essential part of my life. But I don't think it was a key to the researches I've done. I don't think it's that essential.
Right. And
the Russians have done quite well scientifically. They're segregating their scientists and their teachers.
That's right. Yeah. And you talk a lot about that, including the serendipitous effect of a delayed visa to go to the Soviet Union back in 1961 or so, right? That led you to go to Copenhagen. That's then, right. As you just said, I want to talk about the role of serendipity. You talk candidly about the Nobel Prize and the role that it's had in your life and the ceremony even. I want to get into that later. But you talk about missing out, basically. I mean, it wasn't known that it was going to receive the Nobel Prize in 1988 when you wrote Interactions. But you talk about missing out just barely on the Higgs, discovery or prediction with, and we had on the show recently, I had on Carl Hagen, who has collaborated with my late professor, Jerry Guralnick at Brown University, where I went to graduate school. And the two of them, played an enormous role in the prediction. I wonder, can you take us back to that time? And, in terms of like significance, yes, your name isn't included typically amongst the 7 or 8 co-discoverers of it, but it's clear you were on the track. And how does it feel, first of all, to come up to make a discovery like Electroweak unification or SU2 cross U1, et cetera? How does it feel to make a discovery like that? Know you're the first person on Earth, but know that someone else is probably breathing down your neck, as did happen in the case of the Higgs boson.
Well, funny you ask about that. I was at CERN at the time that Jeffrey Goldstone was talking about spontaneous symmetry breaking in the context of relativistic quantum field theory. And then again, the year after that, he was in Scotland with me at this famous summer school where Higgs was also present. And we had wonderful discussions about the possibility of Electroweak unification, the possibility of using gauge bosons, using Yang-Mills theories to describe the weak interactions. But Peter did not really participate much in these discussions because he was the wine steward. He had to take into account the fact that we were serving Hungarian wines and at a NATO meeting, and we wanted to keep this a bit under the table. It wasn't quite under the table. It was in a grandfather's clock that we stored, a broken grandfather's clock that we stored our Hungarian wines. So he wasn't part of the discussions. And had he been with us, he would work with I'm sure with Jeffrey Goldstone, and they would have come upon the ideas that became those of Higgs and company later on. This is just a year before the Higgs did his thing, and so did Hagen and the other 5 people who have been responsible for the creation of the Higgs mechanism. That was a discovery that I would never have made that discovery because I was not so much up on the details of the formal theory, but it could certainly have been done by Jeffrey Goldstone and should have been done by Jeffrey Goldstone earlier, but whatever.
Yes. All right. You can't win them all, at least when it comes to Nobel Prizes. I want to talk about where we are in physics and whether or not this influence, which I would say, you were a prime, responsible party for, which is kind of coming up with something so beautiful it almost can't be wrong. And I'm speaking about unification. And ever since Maxwell, and even unification of heat and thermodynamics and statistical mechanics is a form of unification, all of these great discoveries in some way that we think about gravity and unification of curvature of space-time, they seem to have beautiful elements to them. And I wonder, are we reaching the end of the line? It's hard to argue that string theory isn't beautiful in a certain sense, but is there sort of a road too far that beauty is no longer capable of providing guidance if it ever was? So I guess the question is, are we too overwhelmed, as Fred Hoyle used to say, with the notion of beauty in our equations?
I don't think so. I think I would follow the tradition that Einstein and others for advocating elegance and beauty. That of Paul Dirac was in that tradition as well. No, I don't think we're done with it at all. I anticipate there will be future discoveries and future even more beautiful syntheses will take place in physics. We need to know so much. What I'm afraid that COVID will have another disastrous effect on science, and that has to do with the funding of useless research, because much of the research that we've been talking about is in fact useless. The Higgs bosons have no practical purpose. K-mesons, strange particles, which
quark, right?
Still have no application and would never will. And many of the things we do per se are useless. Certainly the work that LIGO has been doing, the wonderful discoveries that they have made, the opening up of a new form of astronomy, will have no direct impact on our lives, except the appreciation that we are understanding the world a little bit better each day. There'll be much more. We have so many mysteries, and the question is the funding. The American government traditionally has been generous, but not overly generous with respect to science, and the same is true in Europe and in Japan. But will we continue to fund these forms of useless science, of astronomy, astrophysics, space science, and particle physics? It will seem, perhaps justifiably, to the people of America that more money should be spent on biology. More money should be spent on the means to deal with not only this epidemic, this pandemic, but the many pandemics that will come in the future, because we do understand that as people travel more and more, and we investigate odd corners of the world, we bring back odd diseases, and there are many more odd diseases that will come, and many more pandemics. Much research is necessary to deal with this, so we might encounter a disease that's even worse than what we have now, however bad it may seem at the moment. So money is going to be redirected toward climate change, toward pandemics, and toward other threats to human society. Will there be any left over for doing the kinds of research that we need to do? And that I don't know. Will there be a next accelerator, which is not all that expensive, but it is costly. It is tens of billions of dollars. Will that money appear? Will the Chinese build such a machine? Will the Europeans build such a machine? The Americans have already said they would not.
And what about the value of such a machine, irrespective of who pays for it? When it's not clear, first of all, if there is a natural target for such a machine, aside from bigger is better, which I find that argument falls flat. In the case of the superconducting super collider, and in the case of the LHC, at least the targets were clear, and that there was this missing piece that you talk about back in 1988 that was obvious, not low-hanging in the sense that it was easy, but that it couldn't be otherwise, in the opinions of many people, that the Higgs had to exist and then had to have roughly bounded mass range that was accessible. I think I've heard pitches for the future circular collider that will go back to the Big Bang, or we're not going to get anywhere close to, say, the grand unified epoch that you really ushered in, this notion of grand unification. We'll get to that in a second. How would you proceed if you're this, assuming you took your Nobel Prize winnings and put it all in Bitcoin, and now you're worth trillions of dollars? Still, would you fund such a future circular collider? Which, by the way, they always tell you the price tag to build a project, but from an experimentalist, we always double it for two reasons. One, you have to operate the darn thing. You can't just build a battleship or an aircraft carrier and just, there it is, now we're not going to use it. It's about 10% per year. So in a decade, you spend, you double the cost to operate it. But not only that, when there's no clear target for the future circular collider, as cool as it is, and I don't want to rain on the parade or the income stream of my experimental particle physics colleagues, but how would you deal with it, knowing that bigger is better, but there's no natural target for such a machine? What would you do?
Well, first of all, yes, the Higgs boson cost us about $20 billion if you take into account the operation of the machine for 10 or 20 years, for sure. That may be a lowball estimate, in fact.
Yeah.
So things do get expensive. I can say, what else would you want to do with your money, of course, but there are many good answers to that. My hope is that the theorists will come to the rescue. There is one question which I think is one of the central questions of particle physics, which is not often discussed. And the question is there anything else to observe beyond the standard model? There's many reasons to believe that there should be things, but there's no specific. There was a specific theory once upon a time. There was supersymmetry, which was a nice target, and the target was dealt with properly, and supersymmetry as constituted, as originally invented, is certainly excluded, just as grand unification, as originally configured, has been proven to be wrong.
Is that, sorry, Shelly, sorry to interrupt, but I mean, my understanding is grand unification, we're not adequately energetic enough to test grand unification. If it occurs at 10 to the 16 GeV, we might not have any alternative other than the cosmic frontier. Why do you say that that gut, well, maybe you said as originally constituted, but would you say that still grand unification is sort of ruled out the way that supersymmetry is?
Well, supersymmetry at low energy is certainly ruled out.
Sure, yes.
Supersymmetry was introduced for specific purposes and had acquired other specific purposes, such as the explanation of dark matter. And everything looked very neat, except it doesn't lie in that energy domain. It may lie at some other energy domain, of course, but it would no longer do what it was supposed to do. So that, you can still call it supersymmetry. But yes, supersymmetry as introduced failed, and certainly the expectation was that the proton lifetime would be 10 to the 29th years, and that's been certainly excluded. It's now certainly more than 10 to the 30 or 31 years. There is no specific target, and that's again comes back to the central question. Is there anything else up there? None of these theories tell us whether there is something there. Least of all string theory. They are not able to suggest whether there is something that could be found at the next accelerator. We've never found, well, I still have hopes that the Large Hadron Collider will find something interesting. I am confident that the superconducting super collider, had it not been shot down unwisely by Congress, would have found the Higgs at a much less cost than the eventual cost, and would have pushed us to the energies where I would hope there would be something more, energies comparable to what would be achieved at the Chinese machines and the CERN machine that are mere pipe dreams at the moment.
But just getting back, thank you for that. Getting back to why you say that grand unification is sort of excluded or analogous to low energy supersymmetry being excluded. Why do you say that about grand unification as well?
Well, there's no specific target. Again, it's I say that the original formulation of supersymmetry had a very specific purpose in mind. And it was worth looking for supersymmetric particles, and they didn't find them, and they pushed. It's quite conceivable that even the Large Hadron Collider will produce evidence for supersymmetry at some point, but it won't be the supersymmetry that we imagined. And the same is true of grand unification. The grand unification scale could be higher than 10 to the 16th GeV. We have no way of being sure whether there is such a unification scale. Would I support, again, would you support building, what is it called, the 10 times larger proton decay experiment? And now remember, we've been looking with the current device for over 10 years and finding nothing. And that's telling us that the new machine, the new detector, if it existed, would have no chance of finding proton decay for the first year of its operation.
Right.
Not even an indication of it.
I find it hard to justify instruments that have only a single use case. In other words, even though I helped to create this experiment called BICEP that was looking for inflationary generated primordial gravitational waves, which some hailed as potentially a harbinger and an imprimatur of grand unification. Maybe we can get into that. It has other abilities in addition to just detecting B modes, as if that's not enough, because inflation may not have happened, as you say, grand unification may not have happened. I think we know a lot more about the energetics of unification than we do about 10 to the minus 36 seconds after the Big Bang singularity, perhaps. So I would not spend my money on it if I had infinite resources. Potentially, maybe I would, but in a finite resource planet, unless there are multiple cases. And yes, there are other things that have come out of the LHC, but clearly the Higgs is it's on their masthead. It's what you see. It's the reason that at least initially people were saying, yeah, we spent $10 billion to win a Nobel Prize for this discovery. But I want to talk about, kind of the progress, if that's the right word. It's funny because you mentioned Congress, and it reminded me of an old joke, like, what's the opposite of pro? When someone says, I'll tell you the pros, what's the opposite of pro? And the answer is con. And then you say, well, then what's the opposite of progress? It must be Congress. And that's a dig at our lawmakers in the great city of Washington, D.C. But I want to talk about the lack, or perhaps, maybe I'm overstating your case here. You give kind of a scorecard of where things could be going in the future back in 1988 when you wrote this book, and presumably you wrote it in 87, 88. It does have a description of supernova 1987A, which is obviously another serendipitous discovery. But you have a list of, I think, 9 things, and I want to go over them with you, if you'll indulge me, Shelly, because it's not so often we get to chat. And I think this is such a wonderful thing for young people to think about. What did an eminent scientist think about the big picture questions? Because a lot of what I do is ask people, what would you advise young Sheldon, to use a name of a current hit TV show? What would you advise young Sheldon to work on? So back in 1988, you said, first question, why are there so many basic particles? Do you think we have an answer to that question in the intervening 32?
Not.
Okay. So that's an F. I'm gonna make the scorecard. I'll publish the scorecard.
But remember, the number. It depends on what you think the number is. I don't remember what the number was back then, but today it's down to a couple dozen.
Yes. Yeah. Well, there's 17 elementary particles, including the Higgs, the neutrinos, the quarks. Why are there so many free parameters? And I guess this is like coupling constants. Do you think we've approached a rationale for the proliferation of coupling constants?
We have no answers to those questions. None.
So that's 2 Fs. How do we include gravity in the picture of high energy particle interactions?
Well, the string theorists think that they have an answer to that question, but unfortunately, their string theory doesn't overlap very much with the kind of physics that interests me.
And would you say that the failure to observe supersymmetry and its concomitant relationship to string theory is sort of a significant strike against string theory, or would you?
Not.
No?
Okay. String theory makes no mention of where supersymmetry should live.
Mm-hmm.
So no, that's not it. In no way should that be construed as evidence against string theory.
Interesting. So if God I know you don't believe in God, but if a God handed you a paper and said there is supersymmetry is completely excluded at all energy scales, would that cast any doubt on the legitimacy of string theory?
I'm not quite, that is too hypothetical.
Okay, fair enough. Yep. So you say so I'll give gravity included in the standard model. I'll give that a tentative C. I'll give it a C for now.
Give it a C.
We don't grade inflate, unlike you guys at Harvard and BU. Just kidding. So why are there 3 fermion families?
That's a big question. Why are there three? I don't know. Those are questions. Those are the kinds of questions I would like to have answers to.
Do you think people are thinking about these questions, or are they thinking about like, oh, well, this 17th order correction and a Feynman diagram?
No, 17th order corrections are not my style, but I would love to know why there are three families of quarks and leptons. And I would like to know if they are as identical to one another as we believe. Mm-hmm. Could there be something missing in our plans? And I'm still hoping for an outrageous discovery from the Large Hadron Collider. It could be, for example, the discovery of a new particle that decays into a pair of leptons with the same charge, something like that, which just doesn't fit into the picture at all. And that would lead us to perhaps a new direction.
Mm-hmm. And that brings up the next question. Why are the charges of the fermions the way they are? And I would assume, based on what you just said, we don't have much more clarity about that.
The standard model constrains them to a very high degree. Mm. And so, for example, the integer character of electric charge, the fact that the electric charge and the proton charge are alike, aside from the fact that that had to be if life could possibly exist, that is incorporated within the standard model. We understand that.
Mm-hmm. And why do very large numbers appear to play a fundamental role in our theory? And you say, Dirac emphasized the philosophical view that all numbers that are truly fundamental to physics or mathematics, like pi, or the number of spatial dimensions, 3, should be of order 1, which is to say, neither very large nor very small. Thus, we may reasonably inquire, why do very large numbers play a fundamental role in our theory?
Of course, that's a central problem. Many people talk about the small value of the cosmological constant, and indeed that's mysterious. But to me, equally mysterious and equally large is the ratio between the mass of the top quark and the mass of the neutrino. In fact, those numbers, that's a number of the same crazy order of magnitude.
Yeah, that is true. I haven't think about that. On the opposite end, you ask, is the photon really massless? And I think maybe 32 years we've gotten more credulity that it is perhaps massless. Would you agree?
I think we can agree on that.
Yeah, so that's an A+. I give that an A+ finally. Are neutrinos really massless? That's very interesting.
Answered, very neutly answered, and very satisfactorily answered. All too satisfactorily. Again, it's just 3 neutrino species and a 3x3 mass matrix, and that seems to be the whole picture, despite all the noise about sterile neutrinos and anomalies. I was hoping there were some anomalies, but there don't seem to be any.
Right. Has it surprised you that we've gotten most of the precise quantity? We still don't know the exact mass of the neutrinos. We know that there's 2 different hierarchies they can adopt, but is it surprising that some of the most quantitative results have not come from laboratory experiments, but from cosmological limits?
It's amazing.
Yeah.
It's amazing. And those limits, the cosmological limits, are expected to get stronger, and they're almost strong enough to pin down which hierarchy, which ordering of the masses is correct.
That's right, yeah. And even with the experiments, like I said earlier, one nice thing about the cosmic microwave background polarization measurements that I'm involved with, experiments like the Simons Observatory, we'll not only be able to set constraints or maybe detect primordial gravitational waves, we'll be able to detect the neutrino hierarchy, or at least have a limit on the sum of neutrino masses, which should illuminate.
Well, I'm sure there will be some further constraints, and that's very, very important. Also, another indication of excitement to come is the disparity in experiments measuring the Hubble constant, the Hubble tension.
Yes. I talked about that with Adam Rees last week on the podcast. We had a very interesting discussion with him and Wendy Friedman who you remember was involved with the Hubble Key project. So one of the reasons Hubble was launched was to measure the Hubble constant, which makes sense to us. The reason it has a 2.4 meter diameter mirror is so it could see things like Cepheid variables at great distances. It wasn't known when it was designed, Lyman Spitzer and others designing it, that it would be used to measure supernova, type 1a supernova, which would then reveal the presence of dark energy or accelerated cosmic expansion. But now it's being used by Wendy Friedman and her collaborators to look at really prosaic objects called red giants that have very well understood properties and are not confusion dominated by other stars and pixels and outskirts of galaxies. And she's getting a value, and consistent with Adam Rees and his team looking at Cepheids and even other projects, that's wildly inconsistent at the 5 sigma level with the cosmic microwave background forecast of what the Hubble constant should be today based on the early expansion of the universe, when the universe was very simple. And that's a big surprise. And many people think that's one of the greatest controversies in physics today. What would you say about that?
I would say it's potentially very fruitful. Mm-hmm. If that tension is real, it tells us that we're missing something very important and that our standard model of cosmology is flawed.
Yeah, and has implications for even things like the age of the universe. When I was in high school or college and even graduate school, the value of the Hubble parameter, which is the characteristic inverse of the age of the universe, was unknown at the 100% uncertainty level. In other words, we didn't know if the universe was 10 billion years old in 1989 when this book came out, or if it was 20 billion years old. It's a pretty wide range. And now we know it to the percent level. So cosmology is becoming more and more of a precision science, but hopefully as well an accurate science. You mentioned the existence or lack thereof of magnetic monopoles. And you also wrote a poem, I guess, to Blas Cabrera, my old friend at Stanford University, who detected the magnetic monopole on Valentine's Day, I think 1986 or so, and yet it was never observed again. And you beg him to discover monopole 2. So have we made much progress? I don't know of many experiments looking for magnetic monopoles. It seems to be a very...
Well, there have been many searches in the old days, and they were uniformly negative. And nobody rightly expects that monopoles will be found. Mm-hmm. But there's always that possibility, of course.
And yet, if we do you believe that there? I mean, isn't it true that if there exists a magnetic monopole, it would explain the value of the electronic charge in Dirac's theory?
Well, I don't think it would get. I don't think the existence of the magnetic monopole has anything to do with evaluating the value of the electric charge of the electron. No.
And the last question that you talked about back then as an open question is, does the proton live forever? And I think that we've gotten a lot more clarity about as time has gone on.
A damn long time is what we've learned.
Yeah, that's right.
There's not even an indication of proton decay.
Right. Yes.
But coming back to, it was proton decay that motivated the IMB experiment and the Kamioka experiments. And serendipity has led to many discoveries from these devices. They led to the discovery of neutrino oscillations, both atmospheric oscillations and solar oscillations. They led to the discovery of supernova, consequential discovery of supernova neutrinos that had many consequences. And that's contrary to your statement that why should we spend a lot of money on it? Who knows?
All right. I always say, yeah, that's true, but it's dangerous to bet on serendipity. Of course, yeah, the discovery of the CMB itself, cosmic microwave background, was discovered serendipitously. The discovery of dark energy or accelerated expansion, that was serendipitous. They thought the universe was slowing down, that the universe should be decelerating. And in fact, they found the exact opposite.
I remember Gerson Goldhaber calling me and telling me of this contrary discovery and what could it possibly mean. They were amazed at what they had fallen upon.
So I know we only have a few more minutes of your time. I would be, remiss for me not to talk about views on issues that are very, modern and current, but to get your viewpoint on things like, for example, the multiverse, the anthropic principle. Lenny's a big supporter of that. Your friend Lenny Susskind, who was on the podcast yesterday. What are your views on things like the multiverse, and are they a part of the orthodoxy of physics? Should they be or should they not be?
Well, I'm still of the old-fashioned view that the role of the scientist is to deal with observable phenomena. And by their very nature, the other universes in the multiverse are not observable phenomena. So I would draw a line at that point and disclaim any interest in multiverses or other phenomena that are inconsequential from the point of view of the observable scientists who observe or scientists who measure.
Mm-hmm. And similarly, how would you advise a young Sheldon nowadays? If I'm going to ask you things that of interest that you might pursue or recommend pursuit, maybe your granddaughters or whatever, if they want to go into physics, and then I'd also ask you what outside of physics is fascinating to you for a young Sheldon or Sheldina, I don't know, but to pursue.
Yes. Oh, there's so much in science that is exciting, and personally, I prefer the useless sciences, things that I do and things that you do. I think there's so much more to learn about the universe. Our observations are this remarkable development of the past few decades. The fact that, as you mentioned, that cosmology has become a precise science is extremely important and very exciting. And there's so much more to learn. I wonder if you will ask Barry what the likelihood is that LIGO will be able to measure the Hubble constant.
Yes, I will. Absolutely. Yes. And upgrades to LIGO. They're planning an upgrade. We're going to talk about that tomorrow.
There's a Japanese version, which is coming online or has just come online.
Yeah.
So now there are 3 facilities, four facilities, the 2 American ones and Virgo in Italy. And now I forget the name of the Japanese which has the advantage of being supercooled, of being a cryogenic device.
Yes, that's right. And also with the addition, it's not just more sensitive, but now they can perhaps go after the polarization of gravitational waves and perhaps reveal that they might, that there could be, departures from the understood, accepted dual polarization nature. Also, what are your feelings now, decades later, about grand unification, SU5? Looking back, what do you think its role will be, or will it not have a role, SU5 or something like it, in the future?
I don't know. I told you that one of the things that gave me the greatest joy was being confident that some highly contentious idea like Gell-Mann's Eightfold Way, knowing it was true, and at the same time knowing that others, my colleagues elsewhere, did not believe it. That was a terribly nice feeling, and there were times, many times in my life, when I felt that I knew something that other people don't. At this point, I don't know the answers to any of the questions. I'm waiting for answers. But I'm in myself.
The arbitrage of knowledge. When you know something is going to be borne out, it allows you to make a killing in the marketplace of ideas. What about outside of physics? Are there things, consciousness, simulation hypothesis, so these things that physicists talk about when it's physics adjacent? What things outside of physics interest you?
Well, how could one not be interested in the new advances that are being made in virology, in developing vaccines? These vaccines that we Americans have so far been testing, the two that have been, looking extremely likely to work, are based on absolutely new technologies having to do with messenger RNA.
Mm-hmm.
They're not like the old-fashioned things at all. They're sufficiently new to make it rather difficult to predict whether we can make enough of them to deal with the American population. 20 million by January is not enough. That stuff is very exciting. What they're doing is extremely exciting. I read just yesterday or the day before about the debate about wolves. You surely have read about that, whether we should encourage there to be more wolves so that they can eat the weaker elk or deer or whatever they be, that have developed this terrible, uncurable, prion-moderated disease before the disease spreads to humans. Now, there is absolutely no cure for this disease. Even cooking, I'm told by the New York Times, even cooking the deer does not kill the prions because they never were alive.
Right.
So this is
Well, now you're making me really nervous, Shelly. This wasn't part of the deal. I don't want to have to cancel my elk dinner tonight, but now you're making. What about
deer salami too?
That's right. That's right. No venison jerky for dinner. What about life on other planets? If you had a wager, first of all, I don't think we know enough about it, but do you believe that life is abundant throughout the universe, or is it more like Fermi used to say, where is everybody? If there's
First of all, I'm absolutely convinced that there is life on other planets than Earth.
Intelligent?
Solar system. Absolutely convinced. But just because of the enormous size of the visible universe. So yes, of course, maybe in this galaxy, but if not, we have billions of others to choose among. So yes, there'll be life out there, and there'll probably be intelligent life as well. Well, will we have the good fortune, if it is good fortune, to encounter such life? That, of course, I don't know. This noise about some chemical in the gas of some planet.
Venus, yeah, phosphine, molecule phosphine.
I think that's gone away, in fact.
Well, actually, no. It's we had on one of the code discoverers, Sarah Seeger, across the Charles there at MIT, and her team. They announced a rebuttal to the refutation. So it's very intriguing. I'm going to try and have both teams on the show to debate. I did have a podcast with Sarah Seeger of MIT about this. They're very confident. They say the confidence level has decreased a little bit, but it's not enough to for them to retract the claim whatsoever. So it's a very interesting story about.
And then there are all the watery moons out there that may have some kind of life on them, which they may indeed, and that's going to take a lot of money too. And now, would you spend billions of dollars to make a trip to a moon of Saturn to see whether there's life under the frozen?
Again, my rule is I don't do single purpose experiments. So if it's just to see if there's water, no. If it's just to see if there are other things we can do, if we can learn about extreme, solar system dynamics, planetary formation, things like that, yes, I might consider such a thing. But if it's just to see if there's water or ever was water, billions of dollars, it's hard to justify. But it's very fascinating. What about, have you heard of this simulation?
There's a possibility of finding a second form of life on Earth.
Yes, that's right. Yeah. Well, Paul Davies has been a guest on my podcast, and he talks about the shadow biosphere and kind of using left-handed DNA and all sorts of chiral creatures, et cetera. Yes. Abiogenesis is very fascinating. How did life come from mere, molecules? This
is one of the most exciting questions, the origin of life enterprise.
Yeah.
A lot of people have been working in this, well, maybe a lot, not a lot. A number of people have been working in this direction. Some of the work is very skilled and very impressive, but we've gotten nowhere as yet.
Yeah. Yeah, that is often the case. So of course, you know, if you asked Einstein about the prospects to detect gravitational waves in 1915, he wouldn't have been able to guess that 100 years later, a scant 100 years later to the day almost. Last question just about science, and then I'll ask you a couple questions I ask everybody who comes on the podcast. If you have a couple more minutes, Shelly, is that okay?
Sure, let's go.
Okay, so there's a lot of talk about artificial intelligence. You know, across the river, neighbor Max Tegmark at MIT has written about Life 3.0, artificial intelligence, super intelligence, book by Nick Bostrom, kind of claims that the overwhelming likelihood is that we live in some sort of advanced simulation. I wonder, what do you think about such ideas that the Moore's law application and the inevitable kind of artificial supremacy of, you know, perhaps by quantum computers, that they will lead to the likelihood that we are actually simulated entities that just have this notion, like Descartes used to think about, of being a brain in a vat, really being a brain in a vat, but in reality, we're you know, we don't have any other choice.
No, I don't think we're simulations. That's the realm of science fiction. But on the other hand, I was amazed when computers first began to win at checkers. But I said they'll never win at chess, and then they demonstrated they could win at chess, and I said, of course, but they'll never be able to win at Go. And then they demonstrated that they can beat the best Go players consistently. So there's no question that the competence of computers is growing. Not just Moore's law, but something much more sophisticated with the methods of machine learning that are now being used. And there are those who feel that computers will become sentient and will become smarter than us. Certainly, if they do become sentient, they will be smarter than us. And will this ever happen? And does this pose a danger comparable to that of pandemics and nuclear war and global warming? And the answer to that, in my mind, is no.
Okay, Shelly, you've been so gracious. I just have 3 more questions, if you'll indulge me. The first one relates to something Alfred Nobel did when he wrote his Nobel will. This is my Hanukkah gelt for my kids. This is a chocolate Nobel Prize, unlike the one.
Yeah, I still have a few of those downstairs.
So Alfred Nobel, when he wrote his will, he made one of the requirements the betterment of all mankind. And so it wasn't just a material will where he was giving money to future intellects such as yourself to, you know, discover or invent new things, but they had to benefit mankind. Obviously, you know, what you discovered doesn't make a faster, you know, high-speed internet, but it did enable the betterment of the human spirit to understand the deepest mysteries of mankind and of nature itself. I want to ask you, if you were to write an ethical will in the Jewish tradition, you're supposed to live to 120. That's the age Moses lived to. So when you're 120 and you finally depart this planet, what ethical will would you want to leave? What ethical wisdom, not material, but ethical guidance would you want to give to both your biological children, et cetera, but also your ideological ancestors, or, you know, future offspring?
I don't think I have an answer for that question.
So the next question is going to also go into the future, and that involves Sir Arthur C. Clarke. And you may remember the movie 2001: A Space Odyssey.
I never saw it, but
okay. Well, there are these objects that are basically time capsules, and they're left by some alien civilization, and it's supposed to last for millions of years until humanity discovers it, but also is able to decipher it. So in the opening scene, there are some hominids on the plains of the African savannah, and they discover this time capsule, this monolith, and they can't do anything with it. They try to hit it or whatever. But then later, there's found to be one on the moon, and obviously we've advanced tremendously technologically between 2 million years ago in Africa to get to the moon. So I want to ask you, if you had a billion-year long-lasting time capsule, something that was guaranteed, what would you put in it or on it? How would you want to summarize kind of what humanity is all about, or the achievements of humanity today? Maybe it's in physics, maybe not. That would be kind of something that future civilizations could discover and remark about.
My hope, I can't say prayer because I'm not religious, is that human society will last for, let's say, 1,000 years. I'm not optimistic that it will. There are too many outstanding threats. COVID is an example of the sort of threat that we face. It will not wipe out civilization, but who knows what the next pandemic will do. Species tend to die off, and there's no reason not to think that our species will die off. And we can help it with nuclear weapons, for example, and we can help it by doing this wonderful experiment. The greatest experiment ever performed is to dig up all of the fossil fuels on Earth and burn them and see what happens. We're doing that, and we're beginning to see what happens. And what's happening does not suggest to me that there'll be anyone around in 1 million years, let alone 10,000 years. 1,000 years, maybe. But I'm much more worried about the so-called short term than deep time. I hope there will be a deep time.
And I should point out, you're a member of the board of sponsors of the Bulletin of the Atomic Scientist. Where do you rank, global warming compared to atomic, Holocaust, sort of in terms of existential risks to
both existential risks to society as we know it? A major nuclear conflagration. Not just a random bomb shot off by a pathetic little country, but a real conflagration such as the things we were anticipating between the Soviet Union and the United States would be an end to civilization as we know it. The climate change, the way we're pointed now toward an inevitable 30-foot rise in the sea level, if things go as they are, would certainly end society as we know it. It would end the coastal cities of the United States, for example. It would end the country of Bangladesh. It would totally reform, let alone Holland. It would totally reform human society. And we're on the road toward that. And well, what can I say? My country has not done very much positively over the last 4 years in this direction.
And then the last question I ask all my guests, Shelly, involves not going forward in time. Now we're going to go back in time, and it relates to the name of this podcast. So Sir Arthur C. Clarke had 3 famous laws. The first one was any sufficiently advanced technology is indistinguishable from magic. His second law was for every expert, there's an equal and opposite expert. And his third law is the only way of discovering the limits of the possible is to venture a little way past them into the impossible. And that's the name of this podcast. And so I want to ask you, when you were 20 years old or 30 years old, what seemed impossible back then, but by virtue of your courage became reality? And that you would want to basically give advice to your former self?
I never thought there would be just a Dick Tracy phone, for example. Such a concept was thoroughly inconceivable. I remember as a kid wondering if there would ever be such a thing as television, but impossible things came about. And to my father, skyscrapers were incredible surprises, elevators, airplanes. So the change, what we have seen in our lives, the development, the fact that we all carry around these cell phones and can talk to each other from anywhere, it is utterly amazing. So the change that technology has wrought incredible and unpredictable changes, and technology will continue to do that. I have no doubt of that.
Very well. Well, Sheldon Glashow, Shelly, to some of us, I want to thank you so much for your graciousness and all the inspiration that you provided. I can't recommend this book highly enough, Interactions. It's as relevant now as it was in the late 1980s when I first became aware of it. And as I said, it only took me 32 years, but I'm very glad I finished reading it earlier today. Shelly, thank you so much for spending your time on the Into the Impossible podcast. I hope we get to meet in person someday.
Brian, it's been a pleasure.
If you like this video, please subscribe and check out other videos and interviews I do with a multiverse of magnificent minds on the Into the Impossible podcast. See you next time when we go into the impossible together.
Any sufficiently advanced technology is indistinguishable from magic.